So forwarding, it says forward is forwarding on one specific output port. So this is an example, flooding is an example of a richer or more general action. Instead of sending it on one output port, it can send it on all output ports. Actually, it can send it on a subset of all output ports also. It can say send it on 2, 3, and 4, right? All, send it on all. Flooding means sending it on all in general. And NATs, you've seen, are layer 2 devices that look at layer 3 and layer 4 IP and transport layer information to do address translation, right? We saw how they're swapping port numbers and IP addresses. So generalized forwarding can do all of these functionalities. So SDN is essentially unifying all these functionalities by increasing the level of programmability through a richer match action abstraction compared to the traditional destination-based forwarding paradigm. So here's a concrete example of an open flow controlled network. Here, suppose we want to say that packets, airgrams from host 5 and 6, that's host 5 and 6, that are destined to host 3 or 4 should go first here and then go here, right? Well, in this example, this is not the only option, sorry. There's 2 options. You could first go here, and then go here, or you can take the direct route. But we don't want them to take the direct route for whatever reason, because there's other traffic that needs to flow through. If you want them to take this route, then that's a specific set of forwarding actions across the network. So somebody can look at this whole network and plan such forwarding actions and install flow table rules, match action rules that achieve this as follows. So the first rule above says that the top router, it says that the source address is either H5, host 5, or host 6. Those are the source address patterns, then send it on output port 3. And at this router, we install a similar rule that says the source addresses are H5 and H6 matching, then send it on output port 4, right? And once it gets there, you have a rule that says if it comes in via ingress port 2 and it's destined to H3 or H4, then do those actions. If H3 means 4 on 3, H4 means 4 on 4. So now we have set up these routes in this example for a very specific set of source hosts and destination hosts. We can do this for source prefixes, subnet to subnet. We can do this for a multitude of subnets across the network. Plan all of this in this logically centralized place, and then just push all of this over, all the flow table rules over into the network. So this makes management easy, okay? That's the overall idea. Generalized forwarding summary, match plus action abstraction. It's a sophisticated set of match rules, sophisticated set of actions. It allows you a logically centralized view of the whole network and program network-wide optimal behavior, resource management, firewall functionality, whatever you want in the network, right? Until about 2010, a lot of people had talked about programmability or adding programmability to networks, making them more programmable than just IP data and forwarding. In many different ways. In the 90s, there was a paradigm called active networking, where you could send packets with code in them. Think of it as maybe JavaScript code or some very simple language. Send packets with code in them, and routers will execute that code that you're sending. That customizes how your packets should be treated. Okay. This didn't really latch on. One way to think about it is generalized forwarding. The SDN paradigm is the modern incarnation of various kinds of active networking ideas. If you send packets with code in them, it opens up the door to all kinds of security problems, right? Because knowing what a piece of code is going to do is an undecidable problem in general and hard in practice. So what we ended up doing, it was clear that we need more programmability for better management of networks. So we've gone from sort of having a very ambitious view of what a programmable network ought to be, to one where the programmability has been enriched from traditional destination-based forwarding to a much more general set of match actions. Okay, and As a follow-on to this trend, the more recent trend is increasing this programmability in the data plane even more. So the DOM switches, instead of using OpenFlow like protocol, which is now about almost 10 years old, using that, which also is a restricted interface, you can have a richer version of those types of protocols or languages, an example of which is P4. That is, that's sort of gained traction in the last 3 to 5, or more like 5 years, I would say, 5, 6 years, I would say. Adding even more programmability at the forwarding. The more programmability you add, the more you're slowing down these devices. These devices, remember, have nanoseconds to work on a packet. So the more you add functionality there, the more it's going to slow these things down. Okay, that's all. Yeah. Whoever is managing the network. So internetwork, network of networks. Every network is autonomously managed by its operators. So yeah, the owners of the network.
So it's like they are not using this technology at home?
No, no. Software-defined networking hasn't, to my knowledge, found a use case in how it works. It is meant for operators, network operators, so not for lay people. Right? Yeah. Other questions? So I'm going to leave this last section on middle boxes. It's a fairly easy historical overview section as well. Middle boxes are things that do things to packets. Firewalls are examples of middle boxes in the forwarding plane. Caching along the way, providing richer services in the forwarding plane along the way is what middle boxes are for. They have risen in practical adoption along with SDN. So they're often discussed. SDN is more about the control aspect of it. Middle boxes are doing very specific forwarding plane transformations. I'll leave that for DIY reading and move on to routing algorithms, the last topic I want to cover today. Okay. That's chapter 5. At the beginning of chapter 4, we said at a high level, network functionality is decomposed into a control plane and a data plane. Control is routing. Data plane is forwarding plane. I have very little battery, that's why. Great. Computer died. Anyone have a USB-C power cable? Excellent, thank you so much. While the computer starts up, I'm going to just use the whiteboard, blackboard. Sorry about that. Okay, so we said at a high level, network functionality is decomposed into control plane and data plane, right? We saw extensively how the data plane is working from traditional to the SDN world. How do we compute at the controller now? That thing, that intelligence is the network that resides in the cloud, the SDN world. In the traditional world, is just distributed across the routers. Where is this intelligence that plugs into the forwarding cable, this background slow process. Where is this coming from? That is coming from routing algorithms, okay? So that's the routing functionality. This is true in the SDN world as well as in the traditional forwarding world, okay? What is routing? Routing is the cost of computing a pop from one endpoint in a network to another endpoint in a network. What endpoints are we talking about? In general, host to host, but here's the way to think about increasing layers, subnets. A set of hosts belongs to a subnet. A subnet is identified by a subnet mask, a SIGR prefix, right? The a.b.c.d/x citation. A set of subnets forms a network. This is also referred to as an autonomous system because each network autonomously manages itself. It's owned by an independent autonomous entity. And this, a network of networks, is your internet. Right? So when we say routing, packets are going from some host in the internet to another host in the internet. But we can do routing at different levels of this network as well. You can see, I can see. I can see too. All right, well that boots up. Oh, well it's done. We're computing routes in general from subnets in a single network to other subnets within that network. Across different networks, across the internet, there is another layer of routing atop the subnet level routing within a single network, okay? This hierarchical nature of routing is true both in the old world, which is your per router control plane world. That looks like that, right? Where every router has a distributed control plane, as well as in the new world, which is our SDN world, where the control is outsourced to a logically central place. They're both trying to, for a single network, computing routes from one subnet to another. So from like 128.119/16 UMass subnet to, let's say, the corresponding Princeton campus subnet. That's an example of computing a route. Within a single subnet, there's a different layer 2 link layer routing problem to do. It's much simpler than network level routing. Okay, we'll look at that later. But for now, we'll think of subnets as the endpoints of the routing problem. Okay. We will first look at this level of routing before we look at internet-wide routing. Before we look at inter-network routing. We'll look at subnet to subnet routing within one network. Within the AT&T network, how do you go from Boston to Chicago, right? Actually, even in Boston, there could be a bunch of subnets, right? Chicago is a bunch of subnets. That's the problem we're looking at. We're first going to look at this in the abstract. We're going to follow the principles in practice. We're going to study the problem conceptually, formally, and then we'll look at practical protocols. How do large ISPs, what routing protocols do they run? How do they implement these algorithms? What is the internet's one and only internet-wide internet networking protocol? How does that work, right, across all the 50,000 networks that comprise the internet? So there's two classes of protocols: link state routing protocols, distance vector routing protocols. So let's start with the goal of routing, right? That's path computation. Routing is trying to compute paths from an endpoint to endpoint, host to host in general. But we're focusing specifically at this layer right now and trying to compute good paths. What's a good path? Depends. In general, goodness of a path relates to some notion of cost or some notion of performance. It could be the shortest path, it could be the fastest, most capacitated path, which means the path with the fattest bottleneck link. Least congested, could depend dynamically on the amount of traffic flowing through the network and so on. All these styles of routing protocols exist. Okay? It's a very important problem, right? I'd say this is also a top 5 problem. Most things that the textbooks say the top 10 problems are actually more, I'd say more like top 5 problems. Reliable transport, I said, is one of them. Routing is another one of them. Okay? I'll just introduce this problem, and then we'll look at link state and distance vector in great detail on Tuesday. We represent a network as a graph. Okay? This is fairly simple to understand. What's a graph? A graph is a set of nodes or vertices and a set of edges that connect pairs of those vertices. That's what defines a graph. These graphs have, the edges in these graphs have costs essentially. So here, for example, CWZ, it's saying has a cost of 5. So CWZ, that's the edge that has a cost of 5. And like I said, these costs could be representative of how long they are, how thin they are, or some combination of the two, or how congested they are. What the definition of where do these costs come from, we will put that on the stack for a vector while we look at this problem in the abstract, and then we'll revisit how these costs are actually assigned by network operators. How do they determine how all this traffic from Boston to San Francisco should go through Denver or should go through Chicago if an ISP has multiple points of presence? How do they assign costs such that traffic flows in a certain way through the network? We will look at that after we assume costs have been given to us from God-given costs. Okay? There's 2 fundamentally different ways of doing routing. Routing protocols can be categorized actually along 2 axes. The first of which is whether they're global or decentralized. What's the meaning of global versus decentralized? A global routing algorithm is going to look at the entire picture of the graph. And it's going to make decisions over that entire graph. Decentralized does not mean distributed. All protocols are distributed in their implementation. It's a distributed system, so there's pieces of code running in different places. Decentralized is the design aspect that says that routers are aware only of their immediate neighbors. So the global view says, this is your network. Let's say this is the entire network, okay? And this is node U, this is X, this is B. And this is W, Y, Z, and M. The global view is going to look at this whole graph and run algorithms in this graph. The decentralized algorithm, the decentralized view, is one that looks like this. So in the global model, I can look at the whole graph. I'm aware of the whole graph's topology, all edges, all costs, and I'm going to run a graph algorithm to compute. This is the shortest route from U to Z, as opposed to this or any number of other options. In the decentralized world, this is your view. Each node is aware only of its immediate neighbors and the costs on those links. It knows of the existence of all the other nodes in the network, but it doesn't even necessarily know the topology of the rest of the network, let alone costs on the other edges. That's your decentralized view. Okay? That's one axis. The second axis for classifying network protocols is whether they are slow changing routes or fast changing routes. Slow changing routes might change over a period of like hours, possibly. They might remain relatively stationary over a period of days. They might be statically configured, where if something goes wrong or fails, somebody has to manually program different routes. This is true in the traditional world as well as SDN. Dynamic routing algorithms will be constantly recomputing, automatically adapting to failures. Generally, that's the way we do things. Today's routing protocols are dynamic routing protocols that automatically adapt to failures, load. The two protocols we're going to see in great detail on Tuesday, link state and distance vector. Link state is a global routing protocol. It works with the whole graph. It literally runs Dijkstra along the graph. Distance vector has this view. It's a decentralized routing protocol. Both link state and distance vector are dynamic routing protocols. They're widely used in real-world networks as part of different practical routing protocols, which we'll also see on Tuesday. Okay? That's it for today. Homework 4 is due on Sunday, as we just said. High time you start with project 2. I want to see some activity on PSL.